In this video, you're going to learn all the concepts you need to know about heating curves. So first of all, when you're taking a look at heating curves, it's typically a temperature versus time graph. In this one, we have temperature in degrees Celsius on the side, and we have time without a specific unit there because it's not really too important what the unit of time is, just that time is elapsing as you move from left to right. So at your lowest temperatures, you're going to have your temperature rising as it's in its solid state. Now, in its solid state, it's going to gain some thermal energy. And then after a while, it's going to reach a point where it flattens out. Now, when it flattens out, that's known as a phase change. It's absorbing heat, but it's using that heat to rearrange its molecules to change from a solid to a liquid, which is known as melting. Now, if we're dealing with water, then we would look over to the left and we would have a melting point of 0 degrees. If we had some other substances, that would be a different temperature. So the melting point and the boiling point, which we'll eventually talk about, are some defining characteristics of different substances. So again, we're just using water here as kind of our standard substance. Now, after it completes that phase change, it's going to start to absorb heat once again, and that liquid is going to gain energy and its temperature is going to rise for a period of time. Now, again, it's going to plateau, and as it plateaus, it's absorbing heat still, but its temperature isn't changing because it's using that energy to rearrange itself from a liquid to a gas, which is known as vaporization. And then again, if you look over to the side, you would see something known as the boiling point. This is 100 degrees Celsius for water. And then once it completely changes its phase from a liquid to a gas, then it's going to just be a gas that's absorbing heat and increasing its temperature. So those are the five main sections for a heating curve. Now, if you go back the other direction, you're going to have a gas that's changing into a liquid. That process is called condensation. And then if you go in the reverse direction, again, you just have a liquid that is slanting downward in that green section that's cooling down. And then if it goes from a liquid to a solid, that's known as freezing. Now, there are other processes, kind of like sublimation, like when dry ice goes straight from a solid to a gas. Those we're not going to really discuss too much. Those are a bit of rare cases, anyways. So we have all these different things going on. Again, at our lowest temperatures, at our lowest energy levels, it's starting to absorb heat and its temperature is gaining in this red section over here. In the orange section, it's gaining heat, but it's using that heat to break some of those intermolecular forces and then change phases from a solid to a liquid. And then in the green portion, it's gaining heat to increase its temperature once again. And then it plateaus into the blue section. In that blue section, again, it's gaining heat to rearrange itself into a gas. And then lastly, a gas that is gaining heat and increasing its temperature. Now, for those particular sections, there's some sort of interesting things going on there. Um, in any slanted section, our kinetic energy is going to be rising because kinetic energy is directly related to the temperature, which means the average speed of the molecules is going faster. So the kinetic energy is definitely increasing in all the slanted sections. Now, that's not true for our flat sections because, again, we saw in our flat sections the temperature isn't increasing. It's actually absorbing that heat to break those intermolecular forces and pull those molecules farther apart. So, what we have there in the orange section is an increase in potential energy. And then in the blue section, same thing, increase in potential energy. Now, the way it works is Those molecules that are trying to stick together are getting pulled apart. It's kind of like a spring getting stretched out. And once you stretch a spring farther and farther apart, it's going to have more potential energy stored up in there. So, same thing with these molecules, it has an increase in potential energy during those flat parts. Now, throughout this whole entire graph, what it's doing is going through an endothermic process as it's going from the left to the right. So, as it is heating up, it's an endothermic process because it's absorbing heat, and it is rising in temperature or changing phases because it's absorbing heat from the surroundings. Now, the other way around is called exothermic process. An exothermic process is where it is getting colder because it's releasing heat and losing energy overall. So when you move through this graph, there's a bunch of things going on here. If you were to do some calculations, any slanted region, so we'll say any slanted region where the temperature is going up or down, if you had to calculate the exact amount of energy needed to make those temperature changes, you would use a formula: mass times C, which is the specific heat, times delta T, which is the change in temperature, which is final temperature minus initial. Okay, so mass is just the mass of, we'll say, like the water. C is the specific heat, which is a value tied in with the substance that tells you how much energy it takes to raise 1 gram of that substance by 1 degree Celsius. And then if you were to find a phase change energy value, that would be called EPH, the calculation would be different. Whoops. The calculation would be different because there's no delta T because there's no change in temperature for the phase change portions. So what you would use is you would still use the mass because it matters how much of the substance you have, and you would use a delta H value. The delta H values are specific to the substance. So there's a delta H of fusion for the orange portion for melting or freezing, and there's a delta H for the vaporization and condensation section. So those are called the enthalpy of fusion and the enthalpy of vaporization. So those are for the flat portions of the graph. All right, so I hope that was helpful to you in taking a look at heating curves and breaking down what's going on with the molecules, with the temperature, with the phases, and all of the different regions of the graph. Thank you very much for watching and listening.